Okay, so we're going to look at these specific things, and hopefully you should have received an email already if you're on my mailing list with like some other resources. So people asked for particular things, and they we can't obviously go through all of it in 50 minutes. And so therefore what I did was try to pull together some of the other stuff and give you some other resources. And I'll talk about more help with calculations and things like that at the end. So stick around, because that's going to be potentially very useful to you, because I've got some free stuff that you need to know about, and also some other stuff which is massively discounted at the moment. Okay, so we're going to do limiting and excess reagents, a couple of examples of what we do with those calculations, a bit on atom economy and percentage yield. We're going to look specifically at diluting solutions, because it's something that students find quite challenging. And then we're going to look at experimental errors as well. So experimental errors in particular, how that relates to the numbers, okay? So how that relates to the calculation stuff more than anything else, and how we get specific in exam questions when it comes to how an error might affect our results, that kind of thing. Okay, and anytime, remember, ask questions in the chat. I'm absolutely perfectly happy. There's no stupid questions, because someone might be watching the recording and have the same question and they can't ask it, or someone's in the live lesson and they don't want to ask it. So actually, and you can ask it just to me and I won't tell anybody who asked it. So completely anonymous to you. Okay, so we have this little equation, and the question is about identifying the limiting reagent. So this is not a hard calculation, but I think sometimes students struggle with, how do I show my working? Like, how do I actually explain what we mean by these two terms? Limiting meaning all of it gets used up, and excess meaning there is some left over. So it relies on this relationship that we have a balanced equation, and we know that 1 mole of N2 reacts with 3 moles of H2. So for the start of pretty much all of any calculation question, almost all, not everyone, then the first thing I'm going to do is going to work out the moles of what I have. So one question I get asked in this instance, does it matter that it says kilograms? It doesn't matter in this question. So it could be 200 grams and 45 grams, because they're the same ratio as 200 kilograms and 45 kilograms. It could be 200 tons and 45 tons. However, I don't want students to ever get into the habit of ignoring units. So therefore, my recommendation, unless you are absolutely super hard at calculations, always pay attention to units and convert them if you need to. So it matters not in this question, because I'm looking at ratios and I'm looking at like sort of this much compared to this much, and they're both in mass sort of units. But it does matter if the next question says how many moles of nitrogen are there in 200 kilograms, because the answer is different to how many moles there are in 200 grams. So it's not very difficult to turn kilograms into grams. It just times by 1,000. So I'm going to do my moles is my mass over mR. So my moles of nitrogen is 200,000. Next thing I want to point out is that it's N2, right? It's not N. So the mR of nitrogen is 28, not 14. Okay, so it's a molecule. And that gets me an answer which is not very nice. Next little tip, stop rounding up your numbers in the middle of a calculation. It's absolutely so frustrating. Okay, so we don't do it so often when it's a big number. When it's a small number, students round all the time. So if it was 0.007142, the number of times I see students write just 0.007, just cut it off. 1 sig fig. Don't do that, okay? Leave as many numbers as you can. I'm then going to do the same thing for my hydrogen. So I'm just going to do the moles that I have. Moles equals 45,000 divided by 2, a little bit easier, 22,500. Okay, 22,500 is bigger than the other one, but that's not the only thing I need to take into consideration. I need to take into consideration how they react with each other. So there are 2 ways round that I can do this calculation. They're both right, neither of them is wrong. The easiest one is to look at probably the nitrogen. I think that's probably the one that makes most sense to people. So I've got 7,142 moles-ish of nitrogen. What I'm going to say is how much hydrogen, what is the minimum amount, minimum moles of H2 needed to react with that. So I look at the balanced equation. I take 7,142.86 and I times it by 3 because it's a 1:3 ratio. And that would get me the minimum amount of hydrogen I need is 21,428.6. That is bigger than 21,428.6. So that is the moles of H2 that is used up. And that means that my hydrogen is in excess, which means that nitrogen is limiting. So I work out the moles of each one and then pick one and work out what's the minimum number of moles of the other one that I would need to exactly react. And then compare that with the actual number of moles that I'm told in the question. If I did it the other way round, I could take my 22,500 of hydrogen and divide that by 3 to work out the minimum amount of nitrogen that I would need, which is 7,500. And I would see that I don't have 7,500, I have less than that. And so it still gives me the same result, that nitrogen is the one that there's not enough of, and that hydrogen is the one that there's more than enough of. So you can't always tell by the masses, because obviously I have a bigger mass of nitrogen. You can't always tell by the moles, so just be careful that you don't stop at that point and go, well, 22,500 is obviously bigger than 7,100, because you've got to look at the ratio in the equation. But that's how we show our working and work out what's going on with that one. I'm going to now apply the limiting and excess to a example that students hate, usually. Got to pick things you hate, because otherwise there'd be no point doing them. So this is a question about combustion and gases, and it's quite common, especially in AQA. So sometimes it's multiple choice, sometimes it's not. And it's this idea of finding new total volume of gases in the container. So that means gases of products, obviously, because I'm making a gas, so we're making that. But a key thing that I should pick out of this question is that I have been given 2 volumes of gases, not 1. So there's like 2 pieces of information. It's like the previous question where I had a mass of nitrogen and a mass of hydrogen. Now, if one of them was not in excess, I wouldn't need to know the mass of both of them or the volume of both of them, because a different way to write the question that you've probably seen if you've done some practice would be 3 decimeter cubed of ethane was reacted with an excess of oxygen. And then I don't need to know about the oxygen because I'm only working with the ethane. But that's not true in this question. I've been given volumes of both. The other thing to think about is, do I need to change the volumes into moles? Because I told you moles are really important. We should always turn things into moles. Nope, not in this case. If I was going to change masses into moles, then I divide by MR, and MR is different for everything. But if I'm going to change volumes into moles, I'm going to just divide by the same number every time, because the volume of 1 mole is the same if everything's at the same temperature and pressure. So there is no point dividing everything by the same number, because that's just going to give me it's just an extra step that I don't need to do. So what I actually want to know is, let's say I have 3 decimeter cubed of ethane. What is the minimum volume of oxygen needed? So it's back into that idea of using the balanced equation of like, well, how much oxygen do I need to react with 3 decimeters cubed? Is it 21, or is it less than 21, or is it more than 21? That will make me identify, like, is there going to be any ethane left, or is there going to be any oxygen left after this reaction has happened? Because I need to know for total volume of gases, plural, how much is left. So the ratio is 2 to 7. I don't have 2 decimeter cubed of ethane. It's not that nice a question. I've got 3. So to get from 2 to 7, I divide by 2 and times by 7, which is the same as times in by 3.5. So I take 3 divided by 2 times it by 7, or times it by 3.5. And I found out I need the minimum volume of O2 needed equals 10.5. So just using the molar ratio, taking 3, divided by 2 and times by 7, that's what I did to get that. Okay, that's a lot less than the actual volume of oxygen that I have. So oxygen is in excess. Hopefully, if the question has been written properly, oxygen in this situation will always be in excess, because you can't burn completely in oxygen unless you have an excess of oxygen. That's what incomplete combustion is, and that's not burning completely. So it should be written so that the oxygen's in excess, by the way. So that's kind of helpful when you're doing the calculation. But some people write really rubbish questions. Don't count on it. So 10.5 decimeter cubed, that's used up. 3 decimeter cubed of ethane is also used up, because that's the limiting. That means I started with 21 of oxygen. So 21 take 10.5 means I have 10.5 of oxygen left that didn't react, because it didn't have enough ethane. Then I just need to work out how much CO2 I made, and that's just a sort of hopefully relatively straightforward, just using the moles in the equation. So I start with 3. I'm going to use that one because that's the limiting one. That's ethane. I'll write this again because it's a bit. 2 moles of ethane makes 4 moles of CO2. So that's 3 moles of ethane will make 3 decimeter cubed, sorry, will make 6 decimeter cubed of CO2. I'm going to add 6, and that gives me a total final volume of 16.5 decimeter cubed. Not the same as the starting volume. So volume's not conserved, right? It's like moles. The number of moles changes, the volume changes, the total number of atoms doesn't change. That can't, obviously. That's why we balance equations, but other things can change all the time in chemical reactions. I don't include the water. Where did the 6 come from? From the molar ratio. So I know that 3 decimeter cubed of ethane was used up. It's a 2 to 4 ratio, which basically means I make twice as much CO2 as I use up my ethane. So that's just using the moles. And because they are gases and volumes, moles is basically like proportional to decimeter cubed. So I could take 3 over 24 and go, that's how many moles I've got, and then times it by 2 and then times it by 24. But I don't need to do the working out how many moles, because it's just going to be like the same. They are equivalent to each other. I also don't need to include the water because it clearly shows liquid as a state symbol. There are some examples where combustion happens at a higher temperature and the water is considered a gas, but it should be pretty clear from the equation. If that were the case, I would have to add in those moles of water and work out how many decimeter cubed of water I've got. Okay, so volume of gas ones, quite common if you practice them. It's not too much an issue. Wanted to get this going with linking to experiments. Like, when are you going to get asked, apart from this example, which is quite common, when are you going to get asked about excess reagents? And like, why do we do it? As chemists, we get to choose how much usually we add. So why on earth would we add more of one thing that is actually needed? It seems almost a little bit wasteful. So there's lots of different reasons. One is like, go back to that nitrogen and hydrogen and making ammonia. That's an equilibrium. That's reversible. So I'm never going to get like 100% out. But if I increase just one of my reagents, then I can actually make the equilibrium shift to the right, and I can get a better yield. And I don't need to increase both of them. I can just increase like the cheapest one, or the one that I've got more of, and that will get a better yield without spending so much money. So that's one thing I might do. From a practical point of view, so the excess method is where I like literally add too much of something, and I do it to make sure that all my acid reacts, for example. So if I'm adding some magnesium to some acid, I might add more magnesium than I need, and then I can just filter it out. So it's easy to remove. Whereas if I had leftover acid, I can't remove that from the solution so easily. So I might deliberately do it so that one of my things gets all used up. The same with energy changes, or enthalpy changes. If I wanted to measure per mole, say, of magnesium that reacts with acid, again, just take an easy example, then I would make sure maybe that I had an excess of acid so that I knew all of the magnesium reacted. So I need to know like which one I'm calculating the energy change for. And then if you're in year 13 and you've done some rate stuff, you will realize that like if we change in concentrations, let's say there are 2 reactants and I want to change the concentration and see what happens to the rate, then I need the other reactant to not be changing, but it's going to be used up. So if I made it like 10 times more, then it wouldn't be going down as fast and it wouldn't be affecting the rate. So that happens a lot. It's a way of effectively keeping something constant. Moving on a bit, I know some of this is I'm going a little bit fast, but do ask questions, and some of that I've covered elsewhere as well, because I wanted to look at a percentage yield question now. And percentage yield should not be hard, but sometimes it could just be phrased a little bit difficult. Or we maybe look at it and we think, there's a lot of equations going on there. What on earth? How am I supposed to sort of like separate out what's going on? So the main thing about percentage yield is we're looking at what goes in compared to what goes out. So that's what I want to pick out of this question. If you think about any percentage, if you think, oh, I can't remember the calculation, think about how you would calculate your percentage in a test. You would take the amount of marks you actually got, you would divide it by the total number of marks available, and then you times it by 100 to get a percentage. So all we're doing in a chemical reaction is we are measuring in some way how much we actually got compared to what was the maximum we could have obtained based on what we started with. So it's what goes in versus what comes out. So picking out in this question where that information is, it's another one where I have an excess method. So I'm adding an excess magnesium powder. If anything in the question says excess, it means I don't have to do any calculations with it because it's already told me it's an excess and I can ignore it. So the sulfuric acid is the limiting reagent, and that's what I have 0.02 moles of. Doesn't matter how they got to it. I could read all the practical details about filtering things and evaporating stuff, but that's not that important. So acid going in is 0.020 moles. And then what comes out is that thing there, 3.84 of hydrated salt. So hydrated means with the water, because when I make these crystals, they have to have water in them, otherwise they don't make nice crystals. So that mass is including those 7H2A. So it's 3.84 grams. That's what comes out. Now, obviously, hopefully, obviously, I can't just use those two numbers without doing anything else, because one of them's moles and one of them's grams. That's not the same. So to do a percentage, you need to do moles over moles, or you need to do grams over grams. The dot means that the magnesium sulfate is an ionic compound. So you've got like magnesium ions and sulfate ions, and they are ionically bonded to each other. The water is like a covalent compound, so water molecules. And the water molecules are sort of physically attracted to the ions in the magnesium sulfate. And so they're bonded, but we put the dot there to show it's a separate type of bonding. So one is ionic and one is covalent. The only thing that the dot affects is just making sure that we know how to calculate the MR of that whole salt, which is important because I need to know what's the maximum mass of that salt that I can make. And the way that I can do that is using moles times MR. That's how I work out the mass that could be made. So the only thing I need to worry about that dot is, does it affect the reaction? No. When I do the reaction, and if you imagine now, I'm adding magnesium and acid, you can't see the magnesium sulfate because it's dissolved, right? So it's actually, although we write MgSO4, it's separate magnesium and sulfate ions. Then I boil off the water from that solution, concentrate it down, and leave it to further evaporate and cool down, and it will form these crystals. Now, the fact that there's 7 waters, the only thing it's going to affect is the MR. It affects nothing at all about the reaction. So all I need to know is that many moles of acid, it's a 1-to-1 ratio, makes that many moles. So I've got the maximum moles of magnesium sulfate I could make is 0.02. And don't worry, we're going to get onto the MR calculations. That means the maximum moles. So the maximum moles of MgSO4.7H2A is going to be 0.02 because it's all a 1-to-1 ratio. So I'm not counting the moles of water yet. So how we work out the MR is, my pen doesn't like this side of the whiteboard for some reason. We just do MgSO4 like normal. So 1 Mg, 1 S, 4 O's. Add all of that up, it equals 120.4. Trust me. That's that part. Then what I'm going to do is I'm going to take the mass of water, which is 18, so 2 plus 16. I'm going to times it by 7. So 7 times 18, which gives me 126. Dot, as far as you're concerned, because no one's ever going to ask you what that dot means in terms of the bonding, means plus. Don't ever times them, then you're going to get the most ridiculous MR you've ever seen. Add them together, it's just the mass of the MgSO4 plus the mass of 7 molecules of water. Why do I do 7 times 18 instead of 7 times 2 plus 7 times 16? Because the number of times students do 1 times 16 and they forget to times the last one by 7. So I just think of H2O as just like one thing that weighs 18 and times it by 7, and then you're much less likely to go wrong with these calculations. And so the MR is 246.4. I did these calculations earlier. I'm not doing them in my head. And so that the maximum mass, therefore, is moles times MR, 0.02 times 246.4 gives me 4.928 grams. And from there, it's nice and easy to do my calculation. So mass that I actually got is 3.84. Mass that I could have got, the maximum, should be bigger, otherwise we've done something wrong, is 4.928. And the percentage, again, trust me on this one, is 77.9%. I had a question in a previous class about significant figures. I've just done that one in 3 significant figures because it hadn't been told otherwise, and that's a sensible number. If I was told to really use the information in the question, then I might do it just to 2 and round it up to 78, because 0.020 is actually only 2 significant figures. But I'm not going into big detail on sig figs today because we just don't have time to do everything. So percentage yield calculations, fine. So we really just want to know what goes in, what comes out, and we need to compare like for like. So we have to do like mass over mass or moles over moles. So the number in front of the 7H2O doesn't affect your calculations. Well, it has to be included in the mass, right? So when I weigh those crystals, the water is in there. So I have to include it in the MR. Like, I have to know it. And there are lots of other calculations involving hydrated salts, like working out how many molecules of water. So it's definitely part of it. It's not part of the chemistry of the compound, but if I'm working with mass, then the mass of the water has to be included, because that's what I obtained. That's why it said hydrated salt. Okay, so percentage yield. Why is it not 100%? It's not always the same answer. Okay, so what we don't want to do is stock learn. And the one that people tend to learn is they say, well, the reaction might not go to completion, or it might not finish. All the reactants might not get used up. Okay, that's only true for a really small number of reactions, reversible reactions. If I add magnesium to acid, the magnesium is not going to sit there and go, oh, I don't know if I want to react with this acid, actually. Like, no, it's just going to go, right? Most of the chemical reactions that we do in class do go to completion. So there's only a few things you do at A level, like maybe making an ester, where they do sit at equilibrium and not sort of completely react. And in fact, a lot of the time, like the previous question, we used an excess of magnesium to make sure all the acid reacted. So you can't say that the reason we didn't get 100% yield is because not all the acid reacted. That's not going to cut it at all. So why else? Well, most of our percentage yield loss is because of like how we get our product. It doesn't just pop out of the beaker and go, hey, I'm your product. We have to do stuff. So we have to transfer stuff. I had to take that, do some filtering. I had to put it in an evaporating basin. Then I had to get it out of the evaporating basin to get my crystals. I had to get the crystals into a weighing boat. There's constantly moving stuff from one container to another. And all the time, you can't ensure that it all got transferred. If I was filtering something, some of that solution is on the filter paper. The filter paper is not dry. It's got solution on it. So those are places. Distillation, I can't assume when I distill a product, all of my stuff's going to get collected at the end. With my hydrated salts, I had to leave it to make crystals. The same will happen if you're doing an organic practical and you're making some crystals of an organic compound. You can't assume that all of the crystals just appeared. Some of them are still going to be dissolved. So you won't get them. And one that I get frequently as an answer is, oh, impure reactions. You know, maybe it wasn't all magnesium. That is not accepted most of the time, especially if the magnesium was in excess, it made no difference. Again, it's sort of assumed that most of the stuff we're using is quite good quality and we're not. So sometimes it's allowed and sometimes it's not. So best to not use that one. The same with side reactions. Like that doesn't happen very often. There's not an alternate thing that magnesium does with acid, right? It reacts and it makes hydrogen and salt. Like that's what it does. It's not going to decide to make something else. Organic chemistry, I will allow, does sometimes do different things. But generally, it's just separation and purification. Those are the best ones. Okay. Atom economy. I don't want to go over it in a huge detail, just to try and clarify how it's different to percentage yield. So percentage yield is, here's my balanced equation. this is the product that I want. So my salt, my ammonia, whatever. How much did I get out compared to what I put in? So how much did I recover, if you like, out of all those transfer steps and purification steps that I did? Atom economy is simply about, if I were to take that magnesium sulfate example, one of my products was hydrogen and I didn't want hydrogen. So that was just basically, even if I had 100% yield, not all of the massive reactants was useful. So to calculate atom economy, it's really, you don't need to know any details other than the balanced equation. So if I had this as a method of extracting titanium from titanium chloride, so I want pure titanium. So the product I want is going to tell you in the question, what is the product you want? Okay, what is the useful product? You're not expected to know every time, well, which one was I trying to make? It will tell you. So in this case, if it was for making titanium, we write down the atomic mass of titanium from the periodic table, and then we work out the total mass of my 2 lots of magnesium chloride. So the 47.9 is the useful stuff, and the 2 times 95.3 is the wasted stuff. Will they give us the formulas? They'll definitely give you the formulae for titanium chloride. As you go through, there are some things you need to know formula-wise and some that they will give you. Usually in a calculation question, they won't mix that up. So they would normally give you formulae for everything except the most basic acid-base stuff, only because it makes an absolute pain to mark if you've got the wrong formula and then you do all your calculations based on that. And so therefore it is a tendency, for example, to sort of mark those 2 skills separately. So one question, write the balanced equation for this, or give the formula of this. Second question, here's an equation, do the maths. They don't tend to mix them up, because then there's like 20 different possible answers that they have to write in the mark scheme, and that is just takes them too long. But yeah, you've got to remember some formulae. Magnesium chloride, you can work it out from the charges. So how I do the atom economy: useful mass is just titanium, 47.9. Total mass is the titanium plus the magnesium chloride, which is on the bottom. I times it by 100, and I see that this is not a very good atom economy. Does that matter? Possibly not. It really depends on what I want to do with that titanium, and if there's anything else I can do. So how could I make it better? Well, maybe I could find another metal other than magnesium that just weighs less. I actually can't. So like I'm looking, I could do sodium. That's not going to work because I'm going to need 4 moles of sodium chloride because it's NaCl. So actually it could just be that that it's just, that's the best way to do it. The best thing you can do to improve atom economy, there's 2 things. One is an equation where you only make one product, so an addition reaction or something where there's only a useful product. That's quite rare. You can't just change the chemistry. Or find a use for the other product. So if I can find somebody who wants some magnesium chloride and I can sell it to them or use it somewhere else, that becomes 100% atom economy, because now everything's useful. Brilliant question. I was hoping someone was going to ask that. I was taught that atom economy was MR of the product over MR of the total reactants. Guess what? It's a balanced equation. The MR, oops, sorry, I took off my pen. The MR of all the stuff on the left-hand side is exactly the same as the MR of the total stuff on the right-hand side. So it absolutely is, if you think about it, it's a comparison of what you get out that's useful compared to what you put in. So I can understand as a concept teaching divide it by the total mass of the reactants. But as a calculation, since you've already calculated one of them on the right-hand side, you might as well just add up the stuff on the right-hand side, because otherwise you've got to calculate 2 more MR values, which is more adding up. But do you see that because it's a balanced equation, there's the same number of each atom on each side, then the total mass of TiCl4 plus 2 Mg is the same as the total mass of Ti plus 2 MgCl2. It's the same number of every different type of atom that there is, so it's the same total mass. Okay, let's move on from atom economy. It isn't something you need to worry about too much because it's not asked as much as you think. It's usually just one little multiple choice here and there, a little one marker at the end, maybe two. That's about it. This stuff, though, dilutions, comes up a lot because it might be just in a multiple choice like this one. It might be related to a titration question, and it might be related to some sort of practical method, like, for example, colorimetry or acid-base stuff, or the other thing I was going to think, or rates of reaction, where I have an initial concentration and I want to change it to a new concentration. And I have picked this multiple choice question because there are about 3 different places you can go wrong. Yay! So I always think it's good to work through it. I'm not expecting you to just ping me an answer. Don't worry. I'm just, I put the multiple choice answers because it's nice to see where all the different ways that why they've got all those numbers there. Because often people, they do a calculation, they get a number that's one of the multiple choice and they think, well, that must be all right, then I've got a number. But actually all of those numbers are there because they know what you're going to do wrong. Mean, I know. So let's take through what we've got. We've got a volume, we've got a concentration, we've got a formula. That's nice. They didn't have to give you that, but in this case, they've not made it too hard. MgI2. And then they want to dilute it. And I'm going to underline this bit, the iodide ion concentration. Change of wording. Does not say magnesium iodide concentration, says iodide ion concentration. So this is one place where people could split up. And then we got a new concentration that we want. And the question is, how much water would they need to add? So obviously, we can only do these calculations in dilution. So all we want to work out basically is how much more volume do I need? How much more spread out do the particles need to be? So if you get confused by dilution, try to put easy numbers in, such as if I wanted to half the concentration, then I would need to have double the volume, right? So I would have to add the same amount again. So that's one way to put it. If I wanted to go 0.4 to 0.2, I can't change the number of particles, I can only increase the volume, and I would have to double the volume in order to half the concentration, because concentration is moles divided by volume. To double the volume, I would need a total volume of 200. I've already got 100, I add 100. That's sort of the basis of it. So you don't actually need to do mole calculations here, and you don't need to do you don't need to remember a formula. I'm not a big fan of remembering a formula by heart, because actually, well, what if they just ask the question differently next time and you can't use that formula that you memorized so carefully? So it's better to use a little bit of common sense, but it's not all common sense, and some of it I know is quite hard to conceptualize. The first thing that you need to try and understand is the difference between concentration of magnesium iodide, concentration of iodide ions. The best way to imagine that is to use a balanced equation. So there's magnesium iodide, that's the formula. It's ionic. When it dissolves, it breaks up. So all ionic substances break up into their separate ions when they dissolve. So when it goes into water, it is no longer MgI2. The magnesium ions, go their separate ways. And then both of the iodide ions that were attached go their separate ways. So in terms of moles, that's important, because if I started with 0.4 moles of magnesium iodide and I dissolved it, in a deciliter cubed of water to get that concentration, I haven't got 0.4 moles of iodide ions. I've got 0.8. It is a 1:2 ratio. I get twice as much. The best non-chemistry analogy I can think about is if you had 4 cheese sandwiches and you decided to take them all apart, I don't know why, you would have 8 slices of bread, right? You wouldn't have 4 slices of bread because each sandwich is made of 2 slices of bread. So each unit of magnesium iodide is made of 1 magnesium and 2 iodides. So the initial concentration of I minus is not 0.4, it's 0.8. So that's the first sort of easy wrong step we could do in this calculation. Once I've got that, that's my initial concentration. And I want to get that down to 0.25. So I need to know how much I need to dilute that by. I kind of call this the dilution factor. Like, it's going to tell me how much bigger the volume needs to be. So for example, if I wanted to go from 0.8 to 0.4, the volume would have to be 2 times bigger. If I wanted to go from 0.8 to 0.1, the volume would have to be 8 times bigger because I would be diluting it 8 times. This number's not quite so easy to do in your head. Don't do it in your head. You will get it wrong. I trust you. You will. So the way I do it is I do 0.8 over 0.25. It is 3.2 times diluted, 3.2 times smaller, or you can go the other way and say that 0.8 is 3.2 times bigger. Doesn't matter. It means I need 3.2 times the volume. 3.2 times 100 is 320 centimeter cubed. That is my final volume, not my final answer. Careful. Because I didn't start with nothing, I started with 100, and I need to dilute it so it's now 320. That does not mean I add 320, because then I've got 420, and then it's 4.2 times bigger. So if we go back to that initial idea, if I want to half the concentration, I need double the volume, but that doesn't mean I add 200 centimeter cubed. It means I add 100 and I get 200. So 320 is my final volume. 320 take what I've already got is what I need to add. So the answer is B. So 320, answer C, is obviously the answer you could have got where you really paid attention to the iodide, but you forgot about the fact that it's volume added. 160 is where you did 2 mistakes. You forgot about the iodide being different to magnesium, and then you also forgot about it being volume added. And 60 was you decided the final volume was 160, and then you took it away, took 100 away, and so on. So all of those answers could seem like they were really, really feasible. And that's how they get you with multiple choice questions, is the feasible answers. Okay, so calculations, links to experiments, experimental errors, lots of questions. And this is another thing that students ask me lots of questions on, and that's why I wanted to include it. So it's another multiple choice question. Again, I'm not expecting you to necessarily give me an answer unless you're really burning and want to. And it's about titrations, because one thing I've noticed is that this is multiple choice, which is nice because you've got to choose one. But when it's an open question, like what effect will this error have, I get a lot of answers that are the results will be different, or the experiment won't be accurate. Those are totally worthless marks, okay? If a question says, what effect will this have on the experiment, they want to know, like, compared to what you're trying to work out. So in this case, I'm trying to work out a concentration of something. What will happen to that? Will it be bigger or smaller or have no effect? Or will it be a random error? That's what they want to know. So if a question says, what effect will this have on the temperature change? Will it be bigger or smaller or stay the same? That's what you need to focus on when you're trying to link. And so you link what went wrong with which number changes. So you have to actually think about how you would do the calculation and where the numbers go. So if I'm doing a titration, then, okay, acid's in the flask. That's quite important. So acid goes in the flask, and the acid went in the flask from a volumetric pipette. That's what we normally do in a titration. And then the alkali, sodium carbonate, is in the burette. I can draw those, I can't draw that. So, and then how we work it out when we do the titration is we do volume times concentration of alkali. That gives me moles of alkali. And then I do moles of acid based on that. And I do moles over volume is the concentration of acid. So those are the sort of two calculations I do. So basically, a lot of these errors would affect the result, but it's actually asking specifically how, which one of these errors would make the concentration of the acid lower than it should be. So there's two ways that can happen. One is changing the volume of the acid, and the other is changing the apparent number of moles of the acid, which could mean changing the moles of alkali. Okay, so a bubble in air. This is a common question about air in the old burette tap at the bottom. You know, it's really hard to get out sometimes. If the bubble is in your tap and it stays in your tap, then it has no effect. It doesn't matter, because if it stays there, then nothing happens. If the bubble is in your tap and then the bubble moves down and gets pushed out, then your liquid is going down in your burette, but the only thing coming out is air. So what that does is it gives you a bigger volume of alkali than what you're supposed to get, because some of that volume was air. If your alkali volume is bigger, your moles of alkali will be bigger than it's meant to be, which means your moles of acid will be bigger. So basically, it's going to look like you need more alkali than you actually need to neutralize the acid. So it's going to look like your acid is more concentrated than it actually is, because it's going to look like there's more moles of acid in that flask than there is. So the concentration of acid is going to go up. Now let's look at B. So there's a lot of things in titration. We've got to rinse the burette. If we rinse the burette with distilled water, though, some of that water stays in the burette. We've already said things stick to things, so they're going to stay there. If the water stays in the burette, then that means that I've made this really nice, perfect little solution of alkali that I've weighed out carefully and I made in a volumetric flask. When I put it in the burette, some water is going to mix with it. It's going to lower the concentration of the alkali compared to what I think it is. So I calculated the concentration outside the burette, but then I put it in something with water in and it's changed the concentration. So again, that's going to make my acid look like it's more, because my alkali is weaker, or sorry, less concentrated than I thought it was, which means that I'm going to need more of it. And it's going to look like I have more moles of acid because I don't realize that the concentration of the alkali has changed. Then the next one is the one that people think should make an effect, but actually doesn't. And why doesn't it? So anything I do to the burette is a problem, because I'm using the burette to measure the volume of alkali, and that's important. And if I change the volume or concentration of alkali, that's going to change my result. Now let's think about the acid. So my acid is in a container, beaker, whatever. Stick my pipette in, and I take in a nice exact volume of acid, and I transfer it to a flask. Now, what I'm using for the calculation there is the volume of the acid. That's important. And I want to work out the concentration of the acid in that beaker, not in the conical flask. So that's fine, because If I've got water in the flask, I've still got the same number of moles of acid in the flask. It hasn't changed because acid doesn't react with water, so it's not going to get rid of it. The moles of acid depends on the volume that I took out of my pipette. That's the thing that's going in my calculation. The moles of acid is going to get worked out by the alkali. That's not going to change. So if you take 25 centimeter cubed of acid and you put it in a completely dry conical flask, it's going to require a certain amount of alkali to neutralize it. If you take that same 25 centimeter cubed of acid and put it in a conical flask that contains 10 centimeter cubed of water, it's going to require exactly the same volume of alkali to neutralize it. There's no effect because I'm not using the conical flask to measure anything. I'm just using it to observe the reaction. So if there was alkali in the conical flask, that would be a problem because it would use up the acid and that would change the concentration of the acid and change the moles, more importantly. But it's the moles in the flask that's important, not the concentration. However, that pipette, it's really important that I have exactly the right volume because that's going here in my calculation. That is going in. So that is my answer. That was it's a real conceptual workout when it comes to relating things to practicals and stuff like that. And later on in the year, probably Easter time, I'm going to do some free online classes more to do with some practical stuff and also have some resources available for core practicals, like, you know, some practice questions and video walkthroughs to help you out with core practicals, because I do think it's some of the hardest stuff that you find that people find difficult. Speaking of other things, I'm skimming through the next slide because we don't have enough time, so I'm going to whiz on to the next bit. I just want to let you know about stuff because I'm not very good about letting people know about what I do that is free for students and what I do that is just like really low cost stuff for students as well. So if you don't know me, I've been teaching and tutoring chemistry for like 20 years. I've also worked with universities on helping chemistry teachers, like teaching them. I've worked with exam boards like OCR and Edexcel. I've made resources for OCR. I've done examining for both of those as well. And so, you know, I've been around a while. I work from home full time now. I just quit my part-time teaching job last year. I get most of my sort of income from one-to-one stuff. And so, and, you know, I'm fully booked with that. So the stuff that I do with my website is me trying to give back to students that can't afford one-to-one and trying to give other opportunities for you to do stuff, preferably without spamming you too much. And so one of those is the free weekly emails. So it's specific to year 12, year 13 and teachers, which is why I ask people to sign up using the little form just so I can put you in the right group. Because one of the things that I do weekly is a retrieval practice quiz. I think retrieval practice is so important. You've got to keep going back over stuff, otherwise you're going to forget it. And there's just so much at A-level. So one way to just make that easier for you is you get this weekly quiz with the answers that you can just do 10 questions. And then that really helps you go, oh, Christ, I've forgotten that thing that I did last year and I need to go back over it before it's too late. Yeah, before it's like mocks or real exams. And then I send links to other things as well that I think are helpful depending on the time of year, all sorts of different things. So if you're not getting those emails, so like if you think you've signed up, do try a different email address, like maybe not your school email, because school emails are really bad at blocking things. So that's completely free. And then I do stuff that is just kind of low cost. So this time next week, I'm starting my A-level masterclasses, which are live group classes. I say they're live classes. They're not just live classes because for each class, you also get like a checklist, revision materials, practice questions, because I don't think that everyone's going to improve just by like going to one little class once a week. The whole idea is enabling you to do things on your own as well. And so the idea is that you do the practice questions and you get the answers, and then the class focuses on any issues you had, but then also really going into these really harder, exam questions that are more challenging, so that you really get everything covered, because there's no point doing a class going over just basic stuff that you could do on your own in practice questions. They're already really cheap, so they're already like £12 a class if you book a block of 6. But if you book for the next 6 classes before Christmas, it's only £10 a class. So basically it's £60. This is first come, first serve, because I limit it. So I have a maximum of 12 students in a class. It's often less. I'm going to be honest with you. People are slow at this time of year. Come February, March time, those classes are going to be full. There's going to be lots of people asking questions and things like that. But this time of year, it's super quiet because people are like, oh, I'm fine, I don't need it. It's the best time of year to join, therefore, because you're much more likely to get a small class where you can ask more questions and get more detailed feedback and help with stuff. The other thing is that anyone who signs up to anything on my website, whether it be these or whether it be online courses or anything like that, I'm still a teacher at heart, even though I work from home and I do everything online. And I am one of those soft touch teachers that basically, if you are on my website, subscribe to something, then you're one of my students. And that means if you email me with a question, I'm going to answer it, right? So within reason, I've got to eat, I've got to sleep. So there's always that support in between lessons as well. Yes, they are suitable for all syllabuses. So if I get enough demand after Christmas, I will separate it into separate exam boards. But actually, the vast majority of content that's important that you can't revise on your own is completely specific to exam boards. What is different is when it comes near the end, I do predicted paper and exam-based sessions. And obviously, exam technique is slightly different because the papers are just split differently more than anything else. You don't need to remember that code. You will get an email with it in. And then my online course, which I just finished uploading everything today. This is if you really want more on a chemical calculations. As you can see from that list, it is detailed. So I don't do things by halves. There are 8 modules in there. And so it's all completely online in terms of videos, worksheets, answers. Anything that is difficult has video answers, not just mark schemes, because otherwise you just don't always know where the numbers come from. And of course, if you're signed up to an online course and you've got a question, you ask it and I will ask it. So this is, if I show you the kind of level of detail, if I took one of these 8 units, like reacting mass, percentage yield, and atom economy, that's the contents of that. So, separate videos for every little bit that you might find difficult. You may not need all of it because there may be bits like, well, I know how to do that. That's fine. Or you might just want to say, I'm going to skip a video and go to the practice questions. And if I can do them, it's fine. Everyone has a little quiz at the end as well. But you can see that the harder examples also have video walkthroughs so that it's not just a mark scheme. So I've been told off for just completely selling this too cheap anyway. But I'm just I don't care, because I just want people to get better at chemistry. And that is really how most teachers are. They're really more, I have seen some people online who are just obsessed with filling groups, loads of students and charging them loads. And I just want students to do better at their A levels. So for this week only, just because otherwise people forget about it, then it's half price. Actually, that's very slightly less than half price if you do the maths. It's half a penny less. So it's only £24.99. So it's basically the price of half an hour of one-to-one tuition. You get, I think, about 10 hours of videos. I don't know how many hours of practice questions and everything else. And again, you can access it as long as you need to go over it and ask questions. I will be doing other online courses and I will be doing other free stuff. So if you're like, I don't want to pay for anything, thank you very much, that's fine. Not everyone will, I understand that. If you want to help me in a different way that doesn't involve any money, get on the socials and follow me or subscribe. That would be really nice too. So I'm going to need to put some more stuff on YouTube because I've been really slack this half term because it's been manic, but I do have a YouTube channel. I am the CK chemistry that looks like this, not the CK chemistry that looks like the Indian guy. We're quite distinguishable. And then I'm also on all those other ones, Facebook and whatever you want to call the other ones. So find me on there. You know, if you just subscribe, I do put regular content on Facebook and Instagram and that, and I put stuff mostly for teachers on Twitter. But you can also email me if you've got any questions about the stuff, the group classes. I forgot to say they are suitable for all exam boards, and there's a separate class for year 12 and a separate class for year 13. They are starting next Monday. They might be just 1 or 2 students, might be really small. That would be a great thing for you to take advantage of my terrible marketing. Alternatively, I will also be selling recording access if you don't want to attend the live classes or can't. Sorry I went over, but I was trying to give you a lot of detail and for the people that are going to be accessing the link. And I will see you in another free class, no doubt, maybe in the masterclass or wherever. Email me if you have any questions. Brilliant. Goodbye, everybody. I'm going to stop the recording now. Oops.